Hey everyone, Gene here. Welcome back to the channel. Today we're diving deep into Java multithreading, specifically the locking framework. We'll explore key concepts like the ReentrantLock, condition and ReentrantReadWriteLock, and we even throw in some code examples so you can implement these in your own projects. This is the 8th video in my Java multithreading series, so if you missed the last one on synchronizers like countdown latch, cyclic barrier, exchanger, semaphore and phaser, make sure to check it out in the Java Advanced playlist. Let's get started. We will look at codes in this video. Of course, you can pause the video at the right position so that you can follow the code example. That's one possibility. The other possibility is to check out the description of this video. I will post a link there that leads to GitHub where you can find all the codes discussed in this video. Just so you know, it really depends on you what method you choose. Java's locks package provides a powerful framework for managing concurrent access to shared resources. It offers a more flexible and efficient alternative to traditional synchronization mechanisms like synchronized blocks and wait notify. So why is this important? Well, locks give you a finer control over synchronization, including features like timed locks and fair locks. In certain scenarios, these locks can outperform traditional synchronization. They enable more complex synchronization patterns such as read-write locks and stamp locks. Let's take a look at the key concepts. First, we have the locks. These are fundamental synchronization primitives that allow only one thread at a time to access a shared resource. Then we have conditions. These objects allow threads to wait until a specific condition is met before proceeding. We also have read-write locks. These locks permit multiple threads to read a shared resource concurrently, but only one thread to write to it at a time. Then we have stamped locks. These are more advanced locks that offer optimistic concurrency control, which can significantly improve performance in certain situations. Last but not least, we have the lock interface. The lock interface offers a more granular approach to locking than the implicit locks used with synchronized blocks. Key methods of the lock interface are lock, which acquires the lock, blocking the thread until it's available; lock interruptibly, which acquires the lock but can be interrupted; new condition, which creates a condition object tied to the lock for advanced synchronization; try-lock, which attempts to acquire the lock immediately, returning true on success; and there's also another variant of it, which attempts to acquire the lock within a specified timeout; and unlock, which releases the lock. There's one important note. Unlike synchronized blocks, lock operations aren't automatically scoped. You're responsible for acquiring and releasing locks explicitly, often using a try finally block to ensure proper release even in case of exceptions. This flexibility allows for more complex locking patterns, but it also introduces the risk of deadlock and other concurrency issues, so pay close attention because disciplined coding is crucial when using the lock interface. ReentrantLock helps manage synchronization in concurrent programming. Imagine a busy highway with only one lane. Cars need to take turns to pass. In Java concurrency, threads often need to access shared resources, like that single lane. If multiple threads try to access the resource simultaneously, chaos ensues leading to data corruption. Enter ReentrantLock, your traffic cop for threads. It's a powerful tool for managing thread synchronization. Let's talk about its key features. Think of it like a key. A thread can acquire a lock, use the resource and then acquire it again without having to release and reacquire it each time. This is crucial for situations where a thread might need to recursively call a method that also requires the lock. ReentrantLock keeps track of how many times a thread has acquired a lock. It's only released when the hold count reaches 0, ensuring proper synchronization. By default, ReentrantLock is unfair. Threads might acquire the lock in any order, regardless of how long they've been waiting. However, you can create a fair lock that prioritizes threads based on the order at which they requested the lock. This can be useful for situations where fairness is critical, although it might slightly impact performance. ReentrantLock is generally very efficient, especially when dealing with high levels of thread contention. Let's quickly talk about using ReentrantLock. First, create an instance. Decide whether you need a fair lock or an unfair lock. Second, acquire the lock. Use the lock method. If a thread is currently held by another thread, your thread will wait until it becomes available. Number 3 is the critical section. This is where the magic happens. While holding the lock, your thread can safely access and modify the shared resource. No other thread can enter the critical section until the current thread releases the lock. Number 4 is about releasing the lock. Use the unlock method to release the lock and allow other threads to proceed. So the benefits are clear. ReentrantLock ensures that only one thread accesses the shared resource, preventing data corruption and ensuring data integrity. It offers more control than the built-in synchronized keyword. You can implement features like timed locks and interruptible locks. And ReentrantLock provides excellent performance, making it suitable for a wide range of concurrent applications. Let's create ourselves a code example for the ReentrantLock. We have a counter that is incremented by 2 threads concurrently. Without proper synchronization, race conditions could occur, leading to inaccurate results. To prevent this, we utilize a ReentrantLock to ensure that only one thread at a time can access the modified count variable at a time. Okay, let's build the ReentrantLock example. So the first thing that we want to do is create a new class, ReentrantLock example.java, which implements the runnable interface. So right away we can create a run method, which we will use later. We will also need a ReentrantLock, so let's create a new instance for that. And in this example, we're going to count a count variable. So we also need an int variable for that. To increment the count, we create ourselves a new method, increment, which first acquires a lock. And then in a try block, we add 1 to count. And in a finally block, we unlock the lock again. So why do we use try and then finally? Well, in case of an exception, we still have the guarantee that we unlock the lock again, which happens in the finally block. I mean, obviously we could also add a catch block, but we don't need it in this context. Okay, to get the count variable, let's create a getter, getCount, and return the count variable. That's all we need for the structure. Now let's go to the run method and create an instance of this class. ReentrantLock example, counter, new ReentrantLock example. Then we create an int variable, countUtil, which we set to 10,000. So this is the number that we count up to. And then we create a first thread, thread 1, in which we build ourselves a for loop, which counts from 0 until to the variable countUtil. And in every increment, we call the counter.increment. Let's also create a second thread, which essentially does the same thing. Now let's start both threads, and within a try-catch block, we join both of them, meaning we are waiting for both to finish. After having done all that, we print the count number. Okay, so what's the expected result? Well, we count to countUtil twice, which is 10,000. So the result of count should be 20,000, right? So let's put this to a test. Let's go back to the main method and create an instance of ReentrantLock example and run it. And here we can see, after having run the application, the count variable is 20,000. While synchronize is often simpler for basic synchronization needs, ReentrantLock offers greater flexibility and control. Choose ReentrantLock when you require features like fairness, interruptible locks, timed locks, condition variables, or finer-grained control over locking. But what happens when we want to introduce conditions for when locks are lifted? Let's take a look at this in the next example. Now let's talk about condition. Imagine this, you have a shared resource and you want threads to wait until a specific condition is met before they can proceed. The condition interface provides a mechanism for this. So what is the condition interface? It's a key part of Java's concurrency framework. It allows a much finer grained control over waiting and notification compared to the wait and notify methods used with synchronized blocks. Crucially, condition objects are always associated with a lock. This means you can use lock to acquire exclusive access to the shared resource, and then use a condition object linked to that lock to manage the waiting and signaling of threads within that critical section. How does it work? Well, threads can await on a condition object. This effectively pauses the thread until another thread signals the condition. There are several await methods. One that blocks indefinitely until signaled, one that blocks for a specified time, and one that blocks until a specified deadline. When a condition becomes true, another thread can signal the condition using signal, which wakes up a single thread waiting on the condition, and signal all, which wakes up all the threads waiting on the condition. So what are the benefits of using condition? You have much more control over thread synchronization compared to the limited capabilities of wait and notify. It enables complex synchronization patterns such as producer-consumer scenarios, readers-writers problems, and more intricate coordination among threads. Now it's time to see some code, right? We'll take a look at the condition interface from Java's concurrency library. Here we can simulate a producer-consumer scenario. The producer thread adds items to the shared buffer, and the consumer thread removes them from this buffer. Condition objects like isProduced and isConsumed will be used to signal between the producer and consumer threads. Alright, let's take a look at the condition example. For that we create ourselves a new file, conditionexample.java, And the class condition example implements runnable, which also brings us to implement the run method. Now let's start by creating a lock with an instance of ReentrantLock. And from that lock, we pull ourselves two conditions, one for is produced and one for is consumed. Now let's define ourselves a buffer capacity, which we set to 10, and an item quantity, which we set to 100. Then for output purposes, we define ourselves a capacity digits, which we set to 0, and an item digits, which we also set to 0. Then we define ourselves a buffer, in which we set the size of buffer capacity, which is 10. So it's basically an int array of size 10. And then we define ourselves three more variables, which we all set to 0, named buffer size, in and out. So the two main methods that we want to define are one for produce and one for consume. So let's start with the produce method. The first thing that we want to do is make sure we have a lock. Then we create ourselves a try block, and within it we start by creating a while loop, which is true if the buffer size is equal to the buffer capacity, which in other words means the buffer is full. And if the buffer is full, we don't need to produce anymore. And if we run into the case that it is true, we enter an await method. In this case, it's the consumed await method, meaning that at this point we wait for a signal from the consumer. Alright, after the while loop, we put the item number, which was brought through a parameter, into the appropriate place within the buffer. And the appropriate place defines itself by the in variable. And right after that, we add 1 to the in variable, but we also use the modulo of the buffer capacity, meaning that the result within the in variable can never be more than the buffer capacity. So for those that do not know about the calculation of modulo within Java, this can be done with a % character. Alright, after that we add 1 to the buffer size, and then we notify the consumers by executing the signal of the isProduce condition. Once we are done with all that, we define a finally block in which we remove the lock again. Now let's take a look at the consume method. Here we also start with acquiring a lock, and right after that we enter the try block, in which we also start with a while loop, which is true as long as the buffer size is 0, which means that the buffer is empty, and which also means that we cannot consume. There's nothing to consume if there's not a product. After the while loop, we pull out the item value of the buffer, which has the position of the out variable, and we put it into the item variable. After that we add 1 more to the out variable, and again we make use of modulo over the buffer capacity. Next we remove 1 of the buffer size, and after that we notify the producers by executing the signal of isConsumed. And last but not least, we return the item. And right after the try block, we define ourselves a finally block, in which we remove the lock again. Oh yeah, and the consume method returns an int, not a void. Okay, now let's take a look at the run method. First we define ourselves a new instance of this class, and then we define ourselves a new producer thread, which consists of a for loop, which counts from 1 until to the total item quantity that we have. And then within the try block, we produce 1 number per iteration. Let's also create a consumer thread, which also consists of a for loop running from 1 to item quantity, and in every iteration it consumes 1 item. Alright, now let's start both threads and also join both threads to wait for them. The last thing that we want to do is create an output, because until to this point we do the right thing but we don't see anything. So let's quickly define a constructor in which we set the values capacity digits and item digits. And then let's define ourselves a print status method to create ourselves the right output. The last thing we need is to place the print status at the right place within the produce method and within the consume method. Now let's go to the main method and create a new instance of the condition example and run it. And there we can see the entire list of items produced and consumed. And on the right side we can also see how full the buffer is, which has a maximum capacity of 10. So what is the key takeaway? The condition interface provides a robust and flexible way to manage thread synchronization in Java. By combining it with lock objects, you can create sophisticated and efficient solutions for a wide range of programming challenges. There you have it. The condition enables fine-grained control over locks. But what happens if we have many threads reading a value concurrently, while another thread occasionally updates that same value? Let's take a look at how to approach this with a read-write-lock. The ReadWriteLock Interface provides a solution for scenarios where multiple readers are allowed but only one writer is permitted at a time. There are 2 types of locks. The read lock, meaning that multiple threads can acquire this lock simultaneously, allowing concurrent reading. and the write lock, where only one thread can hold this lock at a time, ensuring exclusive access for writing. The ReentrantReadWriteLock offers separate read and write locks. It implements the ReadWriteLock Interface. Okay, in multi-threaded applications, managing access to shared resources is crucial to avoid data corruption. Imagine a scenario where many users are reading from a shared database while a few are updating it. We want to allow multiple readers to access the data concurrently for optimal performance. But we also need to ensure that writers have exclusive access to prevent inconsistencies. This is where the ReentrantReadWriteLock comes into play. It's a powerful tool that provides separate read and write locks. So, as for the read lock, multiple threads can acquire a read lock simultaneously, allowing them to read the shared data without blocking each other. This significantly improves performance in read-heavy scenarios. As for the write lock, only one thread can hold the write lock at a time. This ensures exclusive access for modifications, preventing data corruption. Let's see how to use ReentrantReadWriteLock. You can choose a fair or an unfair lock-in policy. Remember, a fair policy ensures that threads can acquire the lock in the order they requested it, while an unfair policy prioritizes threads arbitrarily. So let's see how to acquire a read or write lock. Use the ReadLock lock method to acquire a read lock, and use the WriteLock lock method to acquire a write lock. To access the shared resource, perform your read or write operation while holding the respective lock. And to release the lock, use ReadWriteLock unlock to release the read lock, and use WriteLock unlock to release the write lock. Okay, it's time for some code again. Let's demonstrate the use of ReentrantReadWriteLock in Java. We'll build a class with a shared integer value. Multiple reader threads can read this value, while only one writer thread can modify it at a time. This can be achieved using separate read-write locks provided by the ReentrantReadWriteLock. Alright, now it's time to create ourselves a ReentrantReadWriteLock example. So for that, let's create a new class and implement the runnable interface. Let's also override the run method right away, because we're going to need it later anyway. Now let's create a new lock of type ReentrantReadWriteLock, and let's also define an int value, which we will use in an instant. So for getting this value, let's create a new method, getValue, in which we start by acquiring a read lock, and within a try block, we return the value. We print the name of the current reader thread, as well as the int value. And we also return the same value. And within the finally block, we unlock the read lock. Let's also create a setValue method, in which we start by acquiring a write lock, and within a try block, we start by printing the writer thread name, as well as the value to set. And after that, we set the value, which was given as a parameter, to the private int variable. And in a finally block, we unlock the write lock. Now let's go to the run method. Here we start by creating an instance of this class, and then we create ourselves a reader thread array of size 10, and then we use a for loop to fill every position with a new thread, which counts from 0 to 99, and in every iteration it gets the value. Now let's create a writer thread of size 5, followed by a for loop, which adds one thread to every position in the array, and in every one of these threads, we count from 1 to 10, and set the value of the iteration index. Now let's start all the reader threads and the writer threads that we have. And after that, let's make sure that we wait for all the threads using join. Alright, that's it. Now let's go back to the main method and create an instance of ReentrantReadWriteLock example and run it. And here you can see all the writer and the reader threads that we have. In this case, most of the readers return 10, but then again, it depends on how you set the application. I think the best thing is if you try it out yourself and play around with those numbers, because the output can be very different on your end. There are important considerations. While ReentrantReadWriteLock offers excellent performance and data consistency, it's crucial to be aware of potential starvation issues. If write operations are consistently prioritized, reader threads may experience prolonged delays in acquiring the read lock. ReentrantReadWriteLock employs pessimistic locking, meaning it assumes that conflicts are likely to occur. This can sometimes lead to unnecessary blocking, especially in scenarios with low write contention. To address some of the limitations of ReentrantReadWriteLock, such as potential starvation and the overhead of pessimistic locking, Java provides another powerful synchronization primitive, the StampedLock. StampedLock offers optimistic locking for reads. This means that readers can attempt to access the shared data without acquiring a lock. If no concurrent modifications are detected, the read operation proceeds without any blocking. This can lead to significant performance gains, especially in scenarios with low write contention and many readers. The difference between StampedLock compared to ReentrantReadWriteLock is that it provides optimistic locking on reads. This results in a much better performance than ReentrantReadWriteLock. In fact, according to Dr. Heinz Kabutz's presentation, Phaser and StampedLock Concurrency synchronizers, StampedLock is 4.43 times faster due to optimistic reads compared to ReentrantReadWriteLock when tested with a single thread. With 4 threads, the factor even moves up times 353. Let's see this in a code example. To demonstrate the use of the StampedLock class in Java, we have a shared resource, an integer value that multiple threads can access. Reader threads attempt to read the value using optimistic locking. If the optimistic read is validated, the value is returned. If not, a pessimistic read lock is acquired. The value is read and the lock is released. Writer threads acquire a write lock, update a value, and then release the lock. Alright, now let's take care of the stamped lock example. Let's create a new class for that, which also implements the runnable interface. And the first thing that we do is define ourselves a variable StampedLock with a new instance of StampedLock. And we also define ourselves a variable of type int, which we will manipulate. Now let's create a new method getValue, in which we start by getting ourselves a new stamp using the tryOptimizeRead method. And then we copy the class value into a local value. Now it's fine if this has worked optimistically, but we still need to validate if it has. And for this we check the stamp using the validate method of the lock. If this returns false, it has not worked. And this means that we need to acquire a pessimistic read lock. So in this case we call the readLock method, which also returns a stamp, which we can save in our local stamp variable. And after that we get the class value into the local value. After having done that, we unlock the readLock in a finally block. Now we print a line to the terminal, which prints the thread name and the value. And last but not least, we return the value. Now let's create the setValue method, in which we start by getting ourselves a stamp acquiring a write lock. And then within the try block, we first print the line of the writer thread name and the value. And then we set the class value with a local value. In the finally block, we unlock the write lock. Alright, now let's go to the run method. Here we create a new instance of this class. And then we create ourselves a reader thread array of size 10. And in every position of this array, we place ourselves a new thread. And in every one of those threads, we count from 0 to 99. And in every iteration, we get the value. Now let's create ourselves a writer thread array of size 5. And then we create ourselves a for loop to place a new thread in every position of this array. And within each one of those threads, we count from 1 to 10 and set the value of the current iteration index. Now let's start all the threads and also wait for all the threads to finish. Alright, that's all we need. Now let's go back to the main method and create a new instance of the StampedLock example and run it. And here you can see all the writer threads and then all the reader threads that all access the value variable. So there you have it. We've explored the Java locking framework, covering key concepts like the ReentrantLock, condition, and ReentrantReadWriteLock. Remember, understanding these concepts is crucial for building robust and efficient multi-threaded applications. Don't forget to like this video if you found it helpful and subscribe to this channel to stay updated on the next video where we'll delve into the world of volatile variables and atomic variables and learn how to choose the right one for your specific needs. Thanks for watching and happy coding!